Hello, welcome to CSC7013, Advanced Math for Computer Scientists. This is Brady Chen. This is Part C of Module 10, the Public Key Cryptography and RSA. In Part A and Part B, we first discussed the basic principles of public key cryptosystems. And we also explained the two different types of cryptosystems. One is called a symmetrical system. The other one is called asymmetric system. The symmetrical system is also called conventional system or private key system. So in the symmetrical system, when sender tries to send a message to the receiver, so basically sender going to encrypt the plain text with a private key, and then the receiver going to decrypt the message using the same key. So basically both sides use the same key. So that's the reason why it's called a symmetrical system, because they use the same private key. Now in the other type of crypto system is called a public key crypto system. Now in the public key crypto system, each user, whether it's a sender or the receiver, they're going to create their own keys. One is called a public key, the other one is called a private key. So they're going to create a pair of keys. So each one going to create his or her own pair of keys. So in the encryption, they're going to use the public key to encrypt the message, the plain text. And then on the receiving side, they're going to use the private key to decrypt the message. Or in another scenario, they could encrypt the plain text using the public key, the private key, and then decrypt it using the public key. So depend on the situation. So then in Part B, we just talked about the RSA algorithm, in which that we create an algorithm to perform the encryption and the decryption. Now, in this part, the Part C, we can actually discuss some of the issues related to the complexity of the algorithms. Now, the algorithm itself is very simple. Now, the key part is the creation of the keys, the public key and the private key. And also, there are certain kind of issues related to the security of the RSA algorithm. And also, we're going to provide a real case for the RSA algorithm. Now, as was discussed in Part B, the most difficult part for RSA is not the encryption and the decryption. The most difficult part is to find a number n, right? And also find the corresponding keys, the public key and the private key. So these are two numbers. Now, in order to find n, we first need to generate two prime numbers, p and q. Okay, prime numbers, and p and q are not the same. Now, we know that in order to make the RSA secure enough, we need to pick the n so that the n is very big number. So how big is the n? It should be, about 1024 bits for the binary number, or equivalently, it should be like 309 decimal digits. Okay. So if we want n to be like 300 decimal digits, then we must pick up the two prime number p and q that bigger enough, right? So when they multiply, they're going to actually get a number of 300 decimal digits. So each p and a q should be around 150 decimal digits. And also q should be around 150 decimal digits. Okay. So in order to make it like a 309, technically should be actually reach like a 155 and a 154. Okay, one of these should be 155 and the other one should be 154. It doesn't matter, it's just a 4 digits difference. Now, how can we find these two prime number? Okay, now this is a very important part of the RSA. Now, to find the prime number, remember we just did the analysis that in order to actually find a number, so with the traditional approach, you have to actually define the number by any number smaller than that number. Now, if you cannot define, that means you can't, this is not a factor for that number. Now, if you choose all the numbers smaller than p and divides the number p, and then no number can divide p, then we can claim p is the prime number. But we know that this is actually, computationally infeasible to do so. Remember that if we use the loop to divide p by all the numbers smaller than p, that's going to take more than a billion years, right? I think it's more than like 10 to the 80 years. That's a huge number. So that's not possible. So we actually introduced an approach called a mirror robin. So the mirror robin is the testing that you're going to start to pick an odd number p. So let's say we're going to pick an odd number p. So the odd integer p at random. So the p should be bigger enough. We should generate the random odd number p, which is about 155 decimal digits. Okay, and then we're going to randomly pick an integer a. So then we perform the mirror robin for a. Test whether p is, a composite, or if we pass the test, that means p is probably a prime number, right? So we actually come out some kind of conclusion that for using mirror robin, you're going to perform the test for p with different random number a, right? If we choose the a and we pass the testing, so then the chance that the p is a prime number is 1 minus 1/4. That's about 75%. Okay, so then we choose another a, different a, right? And it also passes. So the chance that the p is a prime number is 1 minus 1/4 square. The chance is much bigger. It's almost 1/16. Let me see. Oh, 15/16. Okay, so that's close to 90%. Oh, I think it's more than 90%. Okay, so more than 90%. Now, if we pick another a, and the mirror robin, actually we pass the mirror robin again, so the chance that the p is a prime number is 1 minus 1/4 to the cube. So we keep doing the testing. So if we actually test like a t times, or pass the test, then it should be 1 minus 1/4 to the t. So if we pick actually enough, the t enough big enough, so then they all pass the test. Okay, so then the chance that the value p is a prime number, is 1 minus 1/4 to the t. Now we actually did the calculation that if t is a 10, then the chance that this actually a prime number is 99.999%, right? If t is 20, it's 99.99999. I don't know how many nines. It's close. It's almost close to 1. Okay, so the chance is actually almost like a 1. So if we, if p has passed a sufficient number of tests for different a, then we accept a p, even though it's probably not a prime, but we know that it's most likely a prime number. Okay, we accept it as a prime number. And technically, we find out if the p actually passes the Miller-Robbins test multiple times, if the number is sufficiently big, then the number p is actually act like a prime number, even if it's not. So we can accept it as a prime number. Okay, so once we got the p, okay, we accept the p as a prime number, and then we randomly select another odd number, and then we do the same test. So we find the q, right? So we find the 2 prime numbers. Okay, once we find the 2 prime numbers, then we can generate n, which is p times q, and then we can calculate the Euler's-Tortier function of n, which is p minus 1 times q minus 1. And now we can actually select a number, randomly select a number e, which is between 1 and phi of n. Make sure e is, relatively prime to phi of n. So then we got e, and then we calculate d, which says that it's a multiplicative inverse of e modular phi of n. So that's 1. So we find a d. Okay, so we just discussed about this, right? So the key is to find the 2 prime numbers. Okay. Now let's talk about the security of RSA. Now when people try to attack RSA, how they can actually perform the attack? Okay, so there are probably 2 approaches mathematically to attack the RSA. So first, we're gonna pick p and q, right? And then we generate n, which is p times q. Okay. Now we know that the p is big enough. P is approximately 10 to the 155, and the q is approximately 10 to the 154. So the n is in the neighborhood of, some number in the neighborhood of 10 to the 309. So in order to attack it, so they need to, first way they're going to attack it is they try to factor n. Because the attacker knows if someone wants to use the RSA, they have to generate n by multiplying 2 prime numbers. So if they can factor the number n, then they actually find the solution, right? Okay, now as a user, when you generate the n, you can tell people, okay, here's the n I use. Okay, but you have to keep the p and the q secret. You don't want to tell people what's the value of p and the q, because if they know p and they know q, they can easily generate n, because just simply multiply p and q, they will get n. However, if they don't know p, they don't know q, since the p and the q are both actually large prime numbers. So to factor n, remember the story we just mentioned, right? To factor n using the traditional approach, so you have to actually start from the number 2, 3, 4, 5, and divide n by 2, by 3, by 4, by 5, and you can divide the numbers that all the way to half of the n. So then we find out, to find out the facts, it may take up to like more than 10 to the 80 years. 10 to the 80 years. That's okay. That's computationally infeasible to do so. So they should not be able to, figure out what's the P, what's the Q in their lifetime. So that's why it's computationally infeasible to find the P and the Q. So they only have the value n. Now what's the problem of this? Because next step is to figure out what's the phi of n, the Euler's totient function of n. By definition, the Euler's totient function of n is the number of numbers less than n, but relatively prime to n. So in that means, if you want to find the Euler's totient number of n, by definition, you have to test the value n with 2, with 3, with 4, with 5, and all the way to half of the value n. Okay. You have to make sure, okay, are they relatively prime? Are they relatively prime? Are they relatively prime? So they just find out. Now how many times? From 2 to half of n. That's about the same computational time as the factoring n. So that's computationally infeasible to do so. So you have to find the greatest common divisor between n and 2. Okay, that's once. If the greatest common divisor is 1, that means n and 2 are relatively prime. Of course they are relatively prime because n is odd number. Now then you're going to figure out whether n and 3 are relatively prime. So they're going to calculate the GCD for n and 3 if it's 1, and then they figure out whether they are relatively prime between n and 4. So you're going to actually keep doing. If they find out all the numbers from 2 to half of the number n are relative prime to n, then so you're going to continue. You keep doing, okay? Keep going. That's computationally infeasible. So second one they try to attack is if they cannot factor n, like this one, they fail to do the first approach, and they try to do the second approach, determine the phi of n directly without first determining the p and the q. If they find the p and the q, then they know the phi of n is p minus 1 times q minus 1, right? Because they cannot find the p, they cannot find the q, so they cannot determine the phi of n using the formula. But they cannot, then so that's the other approach. If they cannot so they try to determine the phi of n directly without first determining p and q. And this proves to be also computationally infeasible. If they can, so once they got the phi of n, and then because they can easily find the pair of keys, because one of the key is public key, like E. So if they actually already know E, but if they can figure out what's the value of phi of n, the Euler's totient function of n, then they can easily find the multiplicative inverse D of E mod phi of n, because they know phi of n, they know E, so they can determine the D using an algorithm. So then they know both from E, they can determine D. So then that means if one key is public, they can easily determine what's the other key, the private key, if they know phi of n. But we know that based on the definition of phi of n, it's so difficult to do so. So it's again, this is computationally infeasible to do so. And the further approach is also difficult. Determine the D if they know E. E is a public key, right? So they want to actually know E directly without first determining phi of n. That's also proved to be computationally infeasible. So these three are also difficult to do so. So that's the reason why RSA is computationally infeasible to break. So it's a very secure algorithm. Now, here is a real example. So this example is going to give you some idea what kind of algorithm, is RSA, what kind of numbers the RSA is dealing with. So we selected two numbers, odd number. This is the first number P. This is the first number. Now if you think about this number, 1, 2, 3, 4, 5, 6. I don't know what's the number of digits in this number. That's a big number, right? And the other one is Q. Okay. Now, what is N? We can talk about. Okay. N is actually P times Q. Now, to actually perform the operation like N times P times N equals P times Q, now the traditional algorithm never going to work. If you use the algorithm like a Java, Python, or C++ language, now if you try to define a number P, say if I use int P, this is not going to work, okay? Because for enter only allows to define an integer up to like 32 bits. Now for 32 bits, the largest value P we can actually represent is probably 2 to the 32, about 2 to the 32. That's not a big number. Now the number we're talking about is not actually 2 to the 32. We're talking about 2 to the 1024. That's a huge number. Okay. So the P is about 150 digits, and the Q is about the same. So we have two numbers. Okay. So they're different, right? P is 10933 766 109 106 169. Okay, they're two different numbers. Okay, so we can actually, so P is not the same as Q. Now to perform this multiplication, so you cannot even store this number in the regular format. So in Java, you can store a big integer using long. Okay, long actually allows you to store up to 64 bits. Now 64 is still way smaller than 1024. Okay, so the largest number, the long type gonna store is about 2 to the 64. Okay, now we want to actually store the number which is up to 2 to the 1024. Okay, get you some idea. Okay, or for the P, it's half of this number. At least it's a 2 to the 500 and let's see, 12. That's for P. That's for N. And the Q is also about 2 to the 512. So that's P and Q. And we have to use a special defined algorithm. And in Java, now this course, has no prerequisite. So I'm not going to actually talk about the Java. But if you know Java, how to use the Java to program things, now you need to actually use a particular Java class called big integer. Okay, so if you're interested in the big integer, I will create another video and talk about the Java code to actually perform this operation. So in big integer, you can perform the multiplication by calling a method called in the big integer. It's a class. Okay, so big integer is a Java class. Okay, so you can perform the big integer. So you can define the integer which contains like for decimal, you're going to be 150 decimal digits, and another number with about 150 decimal digits, and then you multiply these two numbers, you generate an integer of 300, more than 300 decimal integers, decimal digits. Okay, so that's, you can think about these numbers. So let's see the next slide. Okay, in the previous slide, I actually displayed the two prime numbers, P and Q. Okay, does everyone remember what is the value of P? What is the value of Q? I can't. It's these P and Q are huge number. And then we multiply P and Q to generate N, which is even bigger, much bigger than P and much bigger than Q. So that's a number. So if P is about 150 decimal point digits and Q is about 150 decimal digits, and this N should be around 300 decimal digits. Okay. And then we want to calculate phi of n. Now, if you try to calculate the phi of n from the definition, so you can actually do a lot of work. You're never going to be able to finish in your lifetime. However, since I know n is the multiplication of p and q, and p and q are the prime numbers, so we can actually get the phi of n using the formula p minus 1 times q minus 1. Since p is a prime number, which is odd, so p minus 1 must be an even number, and also q minus 1 must be an even number. So that's an even number. If you look at the digit at the ones place, ones location, that's ones position, that's 8. So not surprising. Okay. Now that's the phi of n. Okay. Now you have to keep that number secret. Okay. Okay. Also, you need to keep the P and the Q private, because if you tell people, oh, these are the two prime numbers I use to generate my n, now people got the P and the Q, then they can generate n. They can actually find out what's the phi of n. So keep the P and the Q private. Never tell people the value, these two prime numbers, and also keep the phi of n private. Okay. You know how to get the number. So you just do the multiplication to get the phi of n. But if they don't know P and they don't know Q, they need to go through the definition. So they're never going to be able to find out phi of n in their lifetime. Okay. Okay. So the next thing we're going to do is we want to pick our public key. So we randomly pick E. Okay. So make sure the GCD of E and the phi of n is 1. So that means E and the phi of n are relatively prime. Remember what's the phi of n? I don't, but I actually displayed this in the previous slide. That's phi of n. But E and the phi of n are relatively prime. How to test this? I just use Euler's theorem, right? Oh, actually, I'm sorry. It's a Euclidean theorem, not Euler's theorem. The Euclidean theorem allows you to compute the greatest common divisor of E and the phi of n, and it should be very quick. Again, it should be very quick. So if I randomly select E and I test this, and I find out, oh, it's relative prime between E and phi of m. So I accept it as one of the key, and I call this the public key. Okay, so the next step I'm going to do is I want to calculate the multiplicative inverse of E modular n. So E times D equals 1 modular n. So that means I want to find D such that E times D modular phi of n is 1. Sorry, this is a phi of n, not an n. Okay. So now if you know phi of m, it should be relatively easy. You can find D in a reasonable time. So you can find the D. And here's the D I find out. Okay. Now you find out if the E is so small, it's not really small, but the value E has how many digits for the E? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. So E is about 10 to the 22. That's a relatively small number. It is not small based on my standard, but it's a small number for the RSA to deal with. And the multiplicative inverse of E, which is D, is huge number. Okay, so I make the E public. Okay, so I keep that one secret. Keep it private. So that's public key, that's private key. Okay, so we generate n. We first generate the two prime numbers p and q, and then we multiply p and q, and we generate n. We calculate the phi of n, and then we generate the first public key e, and then we generate the private key d by finding the multiplicative inverse modular phi of n. Okay. So now we can do the encryption. Okay. So here's my plain text. Now, technically, you can pick a plain text which is much bigger than this number. This is how many digits for this number? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. So it's 21 decimal digits. Now, technically, n is about 10 to the 300 size. So technically, I can pick an m. As far as m is less than n, then any n gonna work. But this m is way too small than compare with n, right? So let's say that's the n I want to, encrypt. So what I do is I'm gonna calculate the m to the power e, m to the e. E is the public key, right? Mod n. N is known to everyone, so you're gonna make it n public. Okay. So e and m to the e mod n, and you generate c. Now what is c? C is this. So this is m. That's the plain text, and that's the C ciphertext. You mail out the ciphertext. Now to decrypt, you're going to perform C to the D. So that's C. Okay, remember that's C. Okay. And what is D? The D is another big number, huge number, mod n. And then I know this is true. I never tested because I actually tested this using the Java big data or big integer. I'm sorry. Okay. So you have to trust it. Okay. Because the Java class big integer going to perform this job for you. And whether this calculation is correct, do you know whether this is really the C? When I do this, you have to have some faith on the algorithm, because technically you're never going to be able to verify by hand. Okay, if you try to get a piece of pencil and try to verify by hand, that's difficult, impossible. So you got to have a faith on the computer algorithm. Okay, so I'm going to actually create another video and showing the Java code to perform these RSA job, perform the encryption and the decryption. Okay, now you will find out the multiplication of these two big numbers are very quick. Okay, it's not super fast, but it's very quick. That's all I can say. Okay, I think that's pretty much all I want to talk about for the RSA. Thank you.